Welcome to my case study presentation. I want to talk to you about finite element exterior calculus, which actually is a follow-up on my last case study presentation where I explained discrete exterior calculus. The idea here is once again to solve PDEs with numerical methods by the means of the theory of exterior calculus. So we basically formulate PDEs using differential forms. And the difference here is to my last presentation is that here we tackle the weak variational form of the PDE and not the strong form as in discrete exterior calculus. So what is this exterior calculus of differential forms again? Really it is a modern formulation of vector calculus. It is in terms of differential geometry, and it allows us to do calculus on Riemannian manifolds. And it unifies all different kinds of integrals and derivatives you know from vector calculus, and then generalizes them to arbitrary dimensions. So a differential K-form you can really think of as being a K-dimensional integrand. So you can have a 1 form, which is a line integrand. So you can integrate it over a curve. You can have a 2 form, which is the area integrand. You can have a 3 form, which is the volume integrand, and so on. And each of these K forms can be integrated over a K-dimensional submanifold. So this is the basic idea. And you can basically think of this K form as being a K-dimensional ruler, which measures K-dimensional spaces. So our ruler varies continuously across the manifold, according to these coefficient functions here in blue. And at each point in space, we locally measure tangential K vectors on this manifold, and globally we measure the whole K-dimensional manifold. And in this way, we have unified the integrals. We can also unify the different kinds of derivatives we have in vector calculus. The gradient, the curl, and the divergence can all be expressed using this exterior derivative. And yeah, this unifies it. And now, combining both the unified integrals and the unified derivatives, we can unify all the major theorems from calculus 2 into Stokes' theorem. Now, we want to do basically finite elements using this theory. And the first thing we do for this is to generalize the PDE domain. We are now solving PDEs on Riemannian manifolds. And FEEC really allows us to treat domains of full topological generality. This means we can have domains with arbitrary number of K-dimensional holes. We can have spheres, we can have toruses, 2 toruses, everything, basically. And we then basically need to somehow discretize our domain. This we do by means of a mesh. And this mesh is something we kind of already know from, for instance, non-PDE, where we use triangles to subdivide a surface. But in higher dimensions, we need different objects. For instance, if you want to subdivide a domain of 3D space, you can use tetrahedrons to subdivide it. And really, our whole manifold becomes what is called a simplicial complex. And this simplicial complex, for instance, for 3D starts with tetrahedron. Then we can take the boundary of our tetrahedron and obtain the faces, the triangles of the tetrahedron. Then we can take the boundary again, and we get the edges. And once again, we get the vertices. And all of these geometric entities are part of our mesh. And in this way, it really preserves the topological and geometric properties of our continuous manifold. Now, to kind of motivate how to do finite element exterior calculus, we first need to look at FEM in vector calculus. So in non-PDE, we mostly only looked at scalar-valued PDEs, where our solutions were scalar fields. But instead, we could also have vector-valued solutions, and then these would be vector fields as solutions. And a good motivation for this are Maxwell's equations, where we have an electric field and a magnetic field. And here the equations don't involve the gradient, but instead the other derivatives of vector calculus, the divergence and the curl. And we now kind of need to define proper Sobolev spaces for these different operators. Because if we take Maxwell's equations and turn them into a variational form, we will have these differential operators under the integral sign, and this tells us that we need new Sobolev spaces. We already know H1, which is the space of scalar fields for which the gradient is square integrable. And one could also call this space H grad. And this now naturally inspires other spaces like H curl and H diff, for which the other differential operators are square integrable. And these spaces are actually very much connected in what is called the de Rham complex. This is the underlying differential structure of our PDE. It connects these different Sobolev spaces by having a Sobolev space in the front, then applying the respective differential operator to it to obtain the next Sobolev space. And in this way, these are connected. And in the end, you also get the L2 space if you apply the divergence. And you can read off some interesting properties from this as well, because if you apply two differential operators in a sequence, you will always obtain 0. So if you first apply the gradient and then the curl, you get 0. And if you first apply the curl and then the divergence, you also get 0. So there is a lot of structure here. And to solve our PDEs correctly and obtain good approximations of our solutions, we need to respect this differential structure of the problem. And we, of course, need now finite element spaces, and they need to be designed in such a way that they respect the de Rham complex. And finite element spaces are really just finite dimensional subspaces of our infinite dimensional function spaces, and for each of these Sobolev spaces, there is one. One we already know is the Lagrangian space, where we have our 10 functions living on the vertices of our mesh, but there are others. For the curl space, we have Nedelec elements, they live on the edges, and for the divergence space, we have Flavia-Thomas elements living on the faces. And these really are constructed in such a way that they preserve the structure of the continuous problem. They form a discrete subcomplex of the de Rham complex, meaning they faithfully represent the differential structure of the problem and therefore provide good discretizations. But really, these spaces are kind of very separate. These all seem very different from each other, and that's unfortunate. And this is really the fault of vector calculus. And maybe we can use exterior calculus to do a little bit better, have some unification, and maybe even extend it to arbitrary dimensions. And the first step for this is to formulate Maxwell's equation using differential forms. The electric field is actually faithfully represented by a vector field. So the dual to it is a one form. This is pretty normal. But in vector calculus, usually the magnetic field is also represented as a vector field, which is actually not really faithful. It is more rather a two form. It's very much related to areal elements and not line elements. And if we now formulate our Maxwell's equations using these differential forms, we now always only have the exterior derivative. So we already have some unification. We can do even better and actually make use of relativistic electrodynamics and formulate Maxwell's equations on the 4D space-time manifold. Because in FEEC, we can easily solve PDEs on manifolds, so this just works. We introduce a Faraday 2 form, a current free form, and we are only left with two equations describing all of electrodynamics. And now, since this only involves the exterior derivative, we really only need one Sobolev space, or one kind of Sobolev space. The Sobolev space of differential K-forms for which their exterior derivative is square integrable. And this is nice unification. And it actually turns out that these Sobolev spaces of differential form are isomorphic to the Sobolev spaces we found earlier. And now we see that the gradient really corresponds to differential 0 forms, the curl operates on differential 1 forms, and the divergence operates on differential 2 forms. Okay? So this is a lot easier. We now just enumerate the k in the differential k form. And now our de Rham complex becomes a lot simpler too. The de Rham complex is now just connected every time by the same thing, which is the exterior derivative, and the space is always just a Sobolev space of differential forms. And our property that two consecutive applications is 0 is now just that twice the application of the exterior derivative to any element gets you 0. And now we can draw an interesting connection to the simplicial complex. The simplicial complex is the thing we saw in our mesh, which started with tetrahedron going to the triangles, the faces of the tetrahedron, to the edges and to the vertices. And this looks very much similar to the de Rham complex. The arrows are in a different direction, the spaces mean something different, and our operators are now boundary operators and not differential operators. But this is like the dual version of each other. And really, this is a really profound insight, where we have a connection between the calculus structure of our PDE, called the cohomology, and the topology of our mesh, the homology. And if we really care about this connection, we are able to correctly discretize PDEs on arbitrary topological manifolds. Now, since we only have one Sobolev space, we only need one kind of finite element space, which is some finite element space of differential forms, and which we call the Whitney K-forms, and these are the differential K-forms which have piecewise linear coefficients. And this is similar to how our piecewise linear Lagrangian space, where we had these 10 functions. These are also just piecewise linear. And we just define it as a span of some basis functions living on the corresponding simplex. So you have this correspondence from the earlier slide between 0 simplices and 0 forms and so on. And this then also tells you where you have to put the basis functions. And so the 0 forms live on 0 simplices, the 1 forms live on 1 simplices, and the 2 form basis functions live on 2 simplices. And you can also now, and these are isomorphic to these Lagrangian, Nedelec, and Ravier-Thomas basis functions. And this also explains why these did live on the edges and the faces. So now it kind of makes a bit more sense, since you can just see that these are the same numbers, really. Okay, and we also, these Whitney K-forms form a subcomplex of the differential form of the de Rham complex, which is great. And actually, since this is so symmetric, you can now easily extend this to arbitrary dimensions, because really you just need to increase this index up here and put more exterior derivatives in between, and the theory generalizes very nicely to arbitrary dimensions. So now you got a theory of finite elements for arbitrary dimensions. And even further, you're not restricted to piecewise linear coefficients for your basis functions, but you can instead have piecewise polynomial of any degrees for the coefficients. So to summarize, what is finite element exterior calculus? Well, it is one thing for sure. It is extremely general. It supports arbitrary dimensions, arbitrary topological manifolds, arbitrary K-forms, and arbitrary polynomial degree finite element solutions. Furthermore, it's a theoretical framework for establishing the well-posedness of PDE problems by respecting this co and homology. And lastly, it's a manual for creating a finite element library of extreme generality, the same generality as FEEC. And this is actually my bachelor thesis. I'm trying to write a Rust implementation of FEEC on coordinate-free simplicial manifold. And if everything goes right, this is going to be my next case study presentation and my last one. Thank you for your attention. Any questions? Yes.
You said that boundary operator squared is 0.
Yes.
But why? Because if you take the boundary of a tetrahedron,
I can quickly show you an example. The thing is, these simplices are always oriented. So if you take a triangle and it has a counterclockwise orientation, and now you take the boundary, you get these edges. And now if you take the boundary again, you get the vertices, but also with an orientation. From this edge, you get -1, +1, but from this edge, you get here a +1 and here -1. And so they cancel out here. So the orientations, by taking the boundary twice, always cancel out. And this is why the boundary operator applied twice to any element will give you 0. because somehow the children of the children are always come in pairs with one positive direction and one with negative direction. So this is just what happens algebraically. But yeah, I guess it's kind of weird. Usually if you have a boundary operator, you don't think so much about orientation. This is basically just an artifact of caring about orientation. Any other questions? Yes? Thank you.
I like the way that you present, so I just wanted to say, I don't thank you because you mentioned non-PDs 3 times. They are going to have nightmares.
Well, I kind of like NumPD, if you couldn't tell, so. I'm sorry for torturing you. Good? Perfect.